Welcome back, fellow cosmic curious cats, to The Catition. I'm your host, here to scratch your scientific itch and purr over the universe's latest revelations. And trust me, folks, today's revelation is so mind-bending, it'll make your whiskers twitch. We're diving headfirst into a discovery that's making astronomers collectively say, "Wait, what just happened?" It's like finding a cat that barks or a fish that flies. It defies all expectations. And it all centers around a truly groundbreaking paper titled A Retrograde Planet in a Tight Binary Star System with a White Dwarf by Ho-Wan Chang, Trifon Trifonov, Man-Hoi Lee, Faustine Contalube, Sabine Reffert, David Rahm, and Andreas Quirenbach. You can find it in Nature, and I highly recommend you check it out, especially if you're into having your scientific paradigms shattered. Now, before we get into the why this is bananas part, let's break down the cast of characters in this celestial drama. Imagine, if you will, the new Octantis system. It's about 72 light years away from us, chillin' in the constellation Octans. And here's the kicker. It's not just one star. Oh no, that would be too simple. It's a tight binary star system. So, we have new Octantis A, which is a K1 III giant star, about 1.6 times the mass of our Sun, but it's really puffed up, like a cat after too many treats, to 5.8 times the solar radius. And then its dance partner, new Octantis B, which is, wait for it, a white dwarf. Think of a white dwarf as the super dense leftover core of a star that's used up all its nuclear fuel. These two cosmic dancers orbit each other with a surprisingly close mean separation of just 2.6 astronomical units. For reference, that's like just a bit further than Mars is from our Sun. Pretty cozy, right? And then the star of our show, the planet itself. This isn't just any planet, folks. This is a gas giant, about twice the mass of Jupiter, chilling out in orbit around new Octantis A. But here's where it gets wild. This planet is in a retrograde orbit. Now, what does retrograde mean? Imagine our solar system with all the planets dutifully orbiting the Sun in one direction. Retrograde is like that one friend who always walks against the flow of traffic. They're going the opposite way. So, you have these two massive stars spinning around each other, and this planet is orbiting one of them in the opposite direction to the star's mutual orbit. This isn't just a quirky orbital preference, it's a huge middle finger to traditional planet formation theories. Because, traditionally, when we think about how planets form, we imagine a big disk of dust and gas around a young star, and everything spinning in the same direction, like water going down a drain. Planets then coalesce from this material, naturally inheriting that prograde, same direction spin. But in a tight binary system like new Octantis, the gravitational tug-of-war between the two stars should, by all accounts, totally mess up any planetary orbit, especially one going the wrong way. It's like trying to juggle 3 flaming torches while riding a unicycle on a tightrope. Mathematically, it just shouldn't work for long. So, how is this rogue planet still out there, defying the cosmic odds? This is where the paper really shines and gives us some fascinating insights. The stability of this retrograde orbit, despite the extreme environment, is a major head-scratcher. One of the key ideas is that this retrograde motion actually stabilizes the planet's orbit. It avoids those nasty resonant gravitational interactions that would destabilize a prograde orbit in such a tight binary. It's like, by being the rebel, it actually found its zen. And then the white dwarf, new Octantis B. Its existence makes the whole story even more complicated and exciting. See, white dwarfs are the remnants of stars that have gone through a dramatic mass loss phase. New Octantis b, our friendly white dwarf, actually started out as a much more massive star, around 2.4 solar masses, and shed about 75% of its mass over 2.9 billion years before collapsing. This past stellar drama, this cosmic shedding, might be key. The paper proposes two mind-blowing hypotheses for how this planet ended up where it is. First, second-generation formation. Imagine the white dwarf as it was dying, spewing out all this material. This material could have formed a retrograde disk, and our planet could have formed from that debris, like a phoenix rising from stellar ashes. How cool is that? The second hypothesis is orbital capture. Maybe the planet originally orbited both stars in a wider circumbinary orbit. But then, when New Octantis b lost all that mass, it destabilized the system, and our planet got gravitationally kicked and captured into its current, wild retrograde orbit around New Octantis a. It's like a cosmic game of billiards, but with planets and dying stars. So, why is this so important? Well, first, it's the first confirmed case of a retrograde planet in a tight binary system. This is not just a neat discovery, it's a tear up the textbooks discovery. It fundamentally challenges our traditional models of planet formation, especially in these close, dynamically active binary systems. It tells us that stellar evolution, like a star dying and becoming a white dwarf, can drastically reshape how planetary systems are built and how they survive. And it also highlights the crucial role of specific geometric configurations, like the near coplanarity of the planet's orbit with the binary plane. It suggests that perhaps nature has more tricks up its sleeve for maintaining stability than we previously thought. This discovery also brings up the fascinating concept of quasi-resonance, or the Kozai-Lidov mechanism. While the paper itself doesn't explicitly state quasi-resonance caused the retrograde orbit in New Octantis, it's a mechanism that can explain how orbits flip and stabilize in complex systems. Basically, the Kozai mechanism is like a cosmic choreographer. It causes a periodic exchange between a planet's orbital eccentricity, how stretched out its orbit is, and its inclination, how tilted it is. In retrograde orbits, this mechanism can actually stabilize things, avoiding those chaotic interactions that would normally send a prograde planet packing. It can even cause orbit flips, taking a prograde orbit and making it retrograde, or vice versa, by pushing the inclination past 90 degrees. So, while we're still figuring out the exact pathway for New Octantis, the Kozai mechanism is a powerful tool in understanding these bizarre orbital behaviors. So, what does this all mean for us, little sentient beings on a tiny blue dot? It means the universe is far stranger, more diverse, and more resilient than we ever imagined. It expands our understanding of where and how planets can form and survive, even in environments we once thought were too hostile. It reminds us that our models are just that, models, and the universe loves to throw us curveballs. This is why we do science, folks, to constantly be amazed, to have our assumptions challenged, and to expand our minds to the incredible possibilities out there. The New Octantis system is a testament to the fact that the cosmos always has more secrets to reveal, and we're just beginning to understand its wild and wonderful ways. That's all the cosmic catnip I have for you today on The Catetition. Join us next time as we continue our journey through the stars, uncovering more perfectly amazing scientific discoveries. Until then, keep looking up and keep being curious.